We've moved from the start of the course from the physical layer, how to get signals to represent data, data link layer, how to make sure that data gets across links. Last topic on the internet and IP addresses about the network layer. How do we get data across the internet? From my computer to some server, some destination computer, anywhere in the internet. So IP allows us to do that by using the IP routing, IP forwarding, and IP addresses. Transport protocols are about getting data across the internet, but we're now moving into how to allow applications to communicate. Say a web server and a web browser. They need to communicate to provide some service to the user. How can we support different applications? We're going to talk generally about transport protocols, quickly about one simple transport protocol, UDP, and a little bit more depth about TCP, because that's the more commonly used protocol. So now we care about getting data between applications, more specifically application processes. You know, maybe you've covered in operating systems or some basic computing course that a software application can be made up of multiple processes, a single process or multiple processes. So in fact, we want to allow one application, say on my computer, to communicate with an application on some other computer in the internet. And those applications are implemented as software processes. So it's about getting data between processes on source and destination hosts. Now we're dealing with the transport protocol and even the higher layer, the application layer. We are dealing with end-to-end communications. With the internet protocol, we send our data from the host, the source host, to a router, to a router, to a router, to the destination host. The routers are involved in that data delivery. In the transport layer, conceptually, we think just about communicating between the source host and the destination host. How do we get from the source to destination? Via routers. But IP does that for us. From the transport protocol's perspective, there's just one source host and one destination host, and we want to allow them to communicate. So we often talk about end-to-end communications or host-to-host communications. The routers are not involved in the transport protocol. There are different transport protocols in the internet. The most popular ones are TCP and UDP. There are others as well. We'll focus mainly on TCP. TCP, the Transmission Control Protocol, is a connection-oriented protocol. Before we transfer data, we set up a connection from source to destination. We do some agreement to set up a connection. It has error control. That is, if something goes wrong, we send some data and it has some errors, we'll retransmit. It has flow control. My destination host is a slow computer. If my source host is a fast computer and can send very fast over the network, then it may overflow the buffers at the destination computer. So to avoid that, we have some flow control where eventually the source will slow down its sending rate. We've seen this concept when we look at data link layer protocols. Stop and wait, the sliding window flow control. TCP implements a variant of those mechanisms. And congestion control. If we send a lot of data into the internet, then maybe the routers become congested. A lot of data is going to routers, the routers slow down. Eventually the routers may overflow and start to drop data. TCP implements some mechanisms so that if it detects some congestion in the internet, it will slow down. So it's quite complex, TCP, but the mechanisms work well so that it is now used by many different applications. Another one is UDP. In fact, UDP is very simple. TCP is quite complex. UDP does not have a connection. Remember, with IP, we do not establish a connection. We just send out IP datagrams. Same with UDP, just send the UDP datagrams. UDP does not have error control. If something goes wrong, too bad from UDP's perspective. No flow control, no congestion control. It essentially does the same thing as IP. Send a datagram, hope that it gets to the destination. If it does, good. If it doesn't, someone else has to deal with that. And in fact, it makes UDP very simple. And in fact, very fast in some cases. And therefore, it may be used for applications where you need to be able to send data quite fast, like voice or video transfer. But it doesn't provide reliability in that if something goes wrong, it will not retransmit. So that's why UDP is not very useful if I want to send an email. Because I send an email and it's 1 megabyte in length, then I want to make sure that 1 megabyte that I send gets to the destination in the same form as how I sent it. So we need some reliability mechanisms, error control. TCP has that, UDP does not. Therefore, email transfer uses TCP, not UDP. There are some things which are common amongst these two and the other transport protocols. In particular, addressing. The ways that we use addresses in transport protocols is common for all of these. And we use this concept called a port. We've mentioned a port before. It's some abstract view of the endpoint for communications, where that endpoint is usually a process, a software process. This is my web browser. It's some piece of software implemented on my computer and running as a software process, and it wants to communicate with a web server somewhere on another computer on the internet, two different software processes. This is the source host and a destination host, and this is our internet. Which can be many routers. So this could be in Thailand, this can be in the US, anywhere in the world. We want to be able to communicate between these processes. We use port numbers to identify which process to communicate with. Because on this computer we may be running a web server, we may also be running an email server, a different software process. This web browser wants to communicate with the web server, not the email server. So we will use port numbers to distinguish that we want to communicate with a web server and not the email server. For example, this would be allocate a port number, and this software may be allocated a different port number. What is it, 25? And when I send something from here, I will set the destination port number to be the software process that I want to communicate with. In this case, my web browser wants to communicate with a web server, not with an email server. So we'll use port numbers to identify the processes on different computers. My computer can have many processes running at the same time, and they can have different port numbers to identify them. So these are the endpoints of the communication. We want to get data from here to here. Most internet applications we use follow a client-server model for communications. One of the applications acts as a client and initiates communications, like your web browser. You open your web browser, you tell it that you want to communicate with some web server by typing in an address of that web server. So your web browser is an example of a client. It initiates communications with some server, the web server. What does a server do? Whether it's a web server, an email server, instant messaging server, other type of server, it normally just sits there, does nothing, until a client initiates communications with it. So the client is active in initiating communications, the server is passive. It does nothing until a client contacts it. So a client contacts a server. Once they've made this initial contact, then data may go in either direction, from client to server or server to client. Many internet applications follow this model that we can identify a client and we can identify one piece of software as a server. In order for this to work, the client must know the address of the server. Because the client, if I want to communicate with a particular server, I need to know its address. The first address I need to know is its IP address. My web browser wants to communicate with a web server on this device. If this computer here has an IP address, in order for my client to communicate with this, I need to know this IP address. So when you open up your web browser, you usually type in a domain name, www.google.com. That domain name maps to an IP address. And that's how your client knows the IP address of the server. We'll talk about domain name systems in the last topic. But we need to know the IP address of this device. In addition, we need to know two more things. We need to know which transport protocol is being used. Is it TCP, UDP, or something else? And each transport protocol is given a protocol number. 6 for TCP, 17 for UDP, 1 for ICMP, and others as well. So the protocol number identifies the transport protocol. If we're using TCP, protocol number 6. And finally, we need to know the port number of the application we want to communicate with. So the client needs to know these three things. What is the IP address of the device I want to communicate with? What is the protocol number of the transport protocol we're using? And what is the port number of the application I want to communicate with? Your web browser normally knows. Your web browser knows that it needs to use TCP, protocol number 6. It knows that most web servers use port number 80. So the only thing you need to tell it as the human user is what is the IP address you want to contact. And you do that by usually typing in a domain name. So you type in a domain name in the web browser address bar. That domain name actually represents an IP address. So now your web browser knows the destination IP address. Your web browser assumes we're using TCP, protocol number 6, and it assumes, unless you say otherwise, that it's contacting a web server on port 80, because that's the default port number used by web servers. If the client knows that information, it can send data to this device via IP. The datagram will get to here, delivered to TCP, and TCP eventually deliver to the web server. And then it can respond. So we have IP addresses, port numbers, and IP addresses, protocol numbers, and port numbers. Protocol numbers are defined per transport protocol. There's a list on this website. These are the most common ones we'll see. Port numbers are defined as well, and there's a list on this website. We have our course evaluations to complete. So let's have a break for 5 minutes, do your evaluation, and then we'll continue on port numbers, because Anne's out here. No reading anymore. Okay. Okay. Do the evaluations and then we'll summarise on port numbers. So we now have different identifiers that we use for our internet communications. Identifiers for hosts or for devices. We use IP addresses. So to communicate with any other computer in the internet, I need to know its IP address. We may use one of multiple different transport protocols. Each protocol has a protocol number. They are fixed. TCP is protocol number 6, UDP 17. If you remember back to the IP datagram header, in the header there was a field for the source and destination IP address. So when we send an IP datagram, I specify the destination IP address. There was also a protocol number field. So in the IP datagram, we specify what transport protocol is being used. We'd set the value 6 if we're using TCP. And in addition, to identify which application we want to communicate with, because our computers may run multiple applications, we use port numbers. Port numbers are 16 bits in length. So we have up to about 65,000 different values. There's 3 different types of port numbers. The port numbers ranging from 0 up to 1023 are referred to as well-known port numbers. These are numbers assigned to common servers, and the assignment is fixed. That is, a web server is assigned the port number 80, an email server 25, and other servers, other port numbers within this well-known list. There's a list of all of them at this website. These are for very common protocols. Web browsing uses HTTP. It's a common protocol that's been around for a long time. And there's some limits by operating systems as to who can use those port numbers. The registered ports, so from 1024 up to 49,000, some of those numbers are also included on this list and include port numbers for less common servers and protocols. That is, you come up with your new server for voice communications. You create your own server, your own protocol for voice communications. Then you may register that port, a port number, as long as it's available, as say 30,163. You would choose a port number that's not used. You would register it with this organisation, IANA, and they would add it to the list of registered port numbers. And that means when someone else on the internet wants to contact your server, if they know they want to contact your voice server, they need to know its port number, which would be on the registered list. And the rest can be used by any application, and normally used by client applications. My web server has a predefined port number, as does my email server. My web browser does not. When I start my web browser, my operating system assigns it a port number. And it normally assigns from this dynamic set from 49,000 up to 65,000. So it chooses a value within that set that's unused, maybe 50,123. My operating system assigns a port number to my web browser. Tomorrow when I start my web browser, it may assign a different value. So it may change. It's not fixed. It's dynamic. But servers, normally the port number is fixed. Why? Because it's the client that initiates communications. The client wants to contact the web server. It must know the port number of the web server. If it's fixed, then it can assume it's port number 80. Once we send something to the server will know the port number used by the browser, because in the message that we send we'll include the port numbers. So normally servers have fixed port numbers, clients have dynamic port numbers. We don't know what the number will be until we start using that software. This diagram shows maybe a little bit better drawn than what I've drawn here, but it's the same point. Our hosts, so our devices attached to the internet, may run different applications at the same time. I'm running a web browser, instant messaging client. I'm running some voice application, making a voice call. And this device is running a web server, an instant messaging application, and also involved in a voice call, all at the same time. We'll use IP addresses to communicate the devices on the internet, protocol numbers to indicate which transport protocol is being used. My web browser may be using TCP, but my voice software may be using UDP. So when this sends data, IP receives that data. Based on the protocol number, it knows which transport protocol to send the data to. And based on the port number, the transport protocol knows which application to send the data to. If it's port number 80, send to the web server. If it's some port number for instant messaging clients, then send to that application. As an example, if we connect to a website, I'll just refresh. So I just connected to the Google website. On my computer, I can see some of the information about that communications I just made with the Google website. So I communicated from my web browser on my laptop to the Google web server somewhere on a computer somewhere else in the world. This just lists that set of communications, or the addresses identified by that set of communications. I had a TCP connection, that is the transport protocol I used was TCP, the protocol was TCP. The address of the local device, my laptop, was 10.10.99.251. That's my IP address. My web browser used a port number 43254. So the web browser was assigned a port number 43254, and I communicated with some other device in the internet identified by 209.85.175.104 and communicating with port number 80, which tells me it's a web server. So here we see those different types of identifiers. IP addresses of my computer, IP address of the destination computer, protocol number, it lists TCP, but it's in fact protocol number 6, the transport protocol being used, and port numbers, followed by the colon here, the port number used by my client application, the port number used by the server application. In fact, I connected to a web server, maybe in the past, and I connected to another server identified by port number 443, which is the port number used when you connect to a secure web server. You know, sometimes you use HTTPS for secure web browsing. That uses port number 443, a different port number. So just an illustration of those addresses in real life. So let's talk about two transport protocols, UDP and then TCP. UDP we'll go through quite quickly because it's reasonably simple. As we said before, it's an unreliable connection-less transport protocol. We don't set up a connection, we don't do retransmissions, we just send our data. My application, I'll draw it again. I have an application on the source host wanting to communicate with the corresponding application on the destination host. Then the application creates some data, sends it to UDP, and UDP puts that data into a datagram, adds a header, and sends it immediately to IP, which then eventually will send it across the internet. It will be received by the internet protocol here via our routers. When IP receives it, it will look at the protocol number in the header. Let's draw our IP datagram. The IP datagram sent by IP, the fields will contain a source address. Let's call this device A and this B. The source is A, destination is B, and the protocol number is the protocol number for UDP. If you go back to one of the previous slides, it's 17. That is in the IP header. UDP will also create a header, and the UDP header will include, we'll see it shortly, but will include the source port number and destination port number. The source port number will be the port number of this application. I'll choose a random value, and a port number of the destination application. Again, I just choose a random example value. So the source port would be 50111 as an example, and the destination port would be 2431. That will be in the UDP header. The IP header will contain the source IP address, the IP of computer A, and the destination IP address, B, whatever the value is, and the protocol number 17 indicating we're using UDP as the transport protocol. We will send this. It'll go across the internet, eventually reach destination B. B will receive it, realizes this is destined to me, check the protocol number. The protocol number says we're using transport protocol 17 or UDP. Send the data to UDP. UDP will check the header and see that the data is destined to port number 2431, and will send the data to the application using port number 2431. UDP does almost nothing else. Take the data, send to IP with a header attached. There's no concept of retransmissions, no concept of flow control or sliding windows, stop and wait. Just take the data, put it in a UDP datagram, send it to IP. IP will deliver, and it will be received and delivered to the application. So it's very simple in terms of a protocol. It does provide a checksum on the packet. That is, the application of the receiver can detect if there's an error. But UDP doesn't provide any way to fix that. Even if we receive some data and detect there's an error in that data, there's no way to ask for a retransmission. So things can go wrong if we use UDP. I could send a UDP segment and it not get to the destination. It could be lost. It could arrive out of order. I send 3 segments, 1, 2 and 3. They arrive in a different order, 2, 3 and 1. They may arrive in error, they may be duplicated even. I send 3 segments, 1, 2 and 3. Something goes wrong in the internet, I receive 1, 2, 2 and 3. I receive segment number 2 twice. That's possible. UDP will not try and fix that. It's up to your application to deal with that. UDP is very simple. It's used by applications that require simplicity. So you need to implement an application that you need a small amount of code, maybe on an embedded system, on a very small device where you have a small amount of memory and processing power. Then maybe you would implement UDP instead of the complex TCP. So some embedded devices will use UDP for communications, for management of those devices. It's used by applications that don't require reliability. Voice and video communications do not require reliability. Because sometimes I can send data containing my voice. If some of that data is not received, then we can still play back that voice and understand what was being communicated. And it's used by applications that require low overheads or high performance in data transfer. Again, commonly voice and video applications that require a low delay. TCP is very complex and can introduce a large delay in communications. This is the UDP segment. It contains an 8-byte header plus data. So the data that we receive from the application, the data here, is placed in this portion of the segment, and we have 4 fields in the header. The source port, for example, 50111, destination port, who we're sending it to, 2431, the total length of the datagram of the segment, so depending upon the size of the data, we set that value, and a checksum, which is an error detection code to check whether there's any errors at the data at the receiver. Do we know the maximum size? The maximum size of a UDP datagram is dependent upon the 16-bit total length. 16 bits gives us 2 to the power of 16 possible bytes in the data. So that's it. Take the data, add the header, source port, destination port, length, and a checksum, send it. If it arrives, the UDP at the destination will remove the header and send the data to the application. That's maybe one of the simplest protocols we'll come across. Just take the data, add a header, send. Nothing else. We'll see how it compares to TCP by going through in some more depth how TCP works. The transmission control protocol. This is the most commonly used transport protocol today. Your web browser uses TCP, your email clients, file sharing applications, instant messaging, file transfer, secure copy when you've done secure shell into the server for the assignment, use SSH or PuTTY, that use TCP. Database applications, you connect to a remote database, will normally use TCP. Some voice and video applications do use TCP. Skype makes use of TCP. So many applications use TCP, the most widely used transport protocol. What does it do? It's a connection-oriented protocol. Before we send data, we establish a connection to the destination. We say, I want to communicate with you, and that one may respond saying, yes, you can communicate with me, and then we transfer the data. UDP is not connection-oriented. UDP is connection-less. TCP is a stream-oriented protocol. What that means is that the data that comes from the application, TCP doesn't care about the contents of that data, it just treats it as a sequence of bytes. So if I want to send a request to obtain a web page, my web browser creates the request, sends it to TCP. TCP just treats that as a sequence of bytes, and we'll see it may split that into 2 TCP segments. Doesn't matter that it's just one message, it may treat it as separate TCP segments. We'll see that in the next few slides. TCP creates a full duplex connection. Once we establish a connection from client to server, then the client can send data to the server and the server can send data to the client at the same time. TCP has reliability built into it, error control. If I send some data and we detect that it's received with an error or it's lost, the source will retransmit. It has flow control. If I send data to the destination and the destination is starting to fill up its buffer, its memory at the receiver, it will somehow tell me to slow down. That's flow control. And congestion control. If I start to send too fast and the internet becomes congested, TCP will slow down. And that's quite complex how those mechanisms work. We'll briefly touch upon flow control. Let's go through these services of what does TCP do. First, in the same way that UDP has a header, TCP has a header to create the TCP segment. We have the data that comes from the application and a header, 20 bytes normally. There are some options that we can include in some cases to increase the length of the header. It includes the source and destination port numbers. The same as UDP includes the source and destination ports, so does TCP. I want to send from my web browser to web server, source port 50123, destination 80. Those values would be set in these 2 fields. A TCP segment contains a sequence number. We saw when we looked at flow control and error control, stop and wait, sliding window, go back N, we use sequence numbers. First segment, sequence number 1. Second segment, sequence number 2. We'll see it's slightly more complex than that, but that's the concept. Identify this data in order of sequence. We saw when we looked at error control that we send data, receive an acknowledgement saying, thank you, I've received that data, please send me the next sequence number. So a segment also includes an acknowledgement number. I send segment 1, it's successfully received. The destination may respond, please send me data with and use acknowledgement number 2, saying the next number expected. So those numbers are included inside the TCP header. Header length, because we may have some optional fields, we need to specify how many optional fields by this field of the header length. Reserved, we don't use. Flags are 1-bit values that indicate the purpose of this segment. We'll explain them on the next slides. Advertised window is used for flow control. Remember with sliding window, we've had an example, we may have 7 segments can be sent, a maximum of 7 segments. We had a window size. Well, in TCP, the destination can set the window size and include it in this field. It advertises the window, the size of buffer that you can fill up at the receiver. So this is used for flow control, advertised window. A checksum, so some error detection codes to check whether there's errors, bit errors in the data received. Urgent pointer is used for a special case. We will ignore that one for now. There may be some optional fields, but we'll not go through any optional fields. And then the data. We'll see some of those, the most important fields, in the examples we go through in the next slides. This describes some of those fields. The flags. No need to draw this diagram, I'll just use it to explain some concept. To remind you, when we looked at flow control and error control, we saw these types of diagrams. The source and the destination. We want to send data from A to B. We said we send a data frame from A to B, and B responds with an ACK frame, an acknowledgement frame. So here we have two types of frames, a data frame and an ACK frame. In TCP, there's just one type of segment, a TCP segment. But we use flags to indicate the meaning of that segment. So there are different, conceptually there are different types of segments indicated by the value of a flag. Let's look at these, well, some of the flags, the ACK flag, for example. In TCP, we just have a TCP segment, and when we respond, it's just another TCP segment. Looks like this. That is, when A sends to B, it's structured like this. It may contain data. When A sends data to B, it must contain data. And when B responds, it sends a TCP segment which has all of these fields in it. How do we know that this is an acknowledgement to this data? That's where the flags are used. The flags are 1-bit values. So there's a number of bits here that we have available. If the value is bit 1, then the flag is on. If it is bit 0, the flag is off. There are different types of flags. They are listed here. Let's look at the acknowledgement flag. If this segment contains just data, then the ACK flag would be set to 0. It is not an acknowledgement. That's what it means, that in the header of this TCP segment, one of the fields is an ACK flag, a 1-bit value. If it's set to 0, it means this is not an acknowledgement. If B responds and it wants to acknowledge the data it received, it sends a TCP segment and it sets the ACK flag to 1 to say this segment is an acknowledgement. That's how flags are used. They indicate the information or the meaning of this message. This message means it just contains data. It is not an acknowledgement. This message means it is an acknowledgement. And there are other types of flags, depending upon different things that we want to communicate between either side. We'll see that when we set up a connection, we'll use the SYN flag to synchronize some sequence numbers. When we close a connection, we'll use the FIN flag to finish the connection. We'll send a TCP segment, set the FIN flag to 1. That tells the other side I want to close the connection. And there are some other flags, but the main ones we'll see are ACK, SYN, we'll see a quick example of FIN, and reset's another way to close a connection, to reset a connection. So if I send a TCP segment to a destination computer with the reset flag equal to 1, it tells that computer, I want to reset the connection. If it's set to 0, then that flag is ignored. It's off. So sometimes I'll mention a TCP ACK. What I really mean, a TCP segment with the ACK flag set to 1. Okay. The other point by using flags is that we can use piggybacking. This TCP segment, the first one contains data. The ACK flag is off. It is not an acknowledgement. This TCP segment, the ACK flag is on. There is no data. We may send a TCP segment that contains data and the ACK flag is on, which really means this segment is a data segment and an ACK segment. It has two meanings. It carries some data and it is an acknowledgement for some previous data that we've received. That's the concept of piggybacking. Let's see how sequence numbers are used in TCP. TCP header contains a sequence number field, 32 bits in length. So our sequence number can start at 0 and has 2 to the power of 32 possible values, after which it comes back to 0 and goes up again and just wraps around. Turns out our acknowledgement number is the same length. When we looked at flow control and error control, we said we send a segment with a sequence number, frame 1, sequence number 1, then 2, then 3, then 4, and when we receive acknowledgements, the acknowledgement says the next sequence number expected. I send sequence number 1, the receiver acknowledges saying I expect to receive segment 2. I send 2 and they say I expect to receive 3, and we can keep going. In TCP it's the same concept, except the sequence numbers identify bytes, not segments. We have an initial sequence number. We don't have to start at 0. I establish a connection. I could start at 0, but in fact TCP allows us to choose an initial sequence number, the first value that we're going to start with. And it's chosen independently at both directions. So node A chooses an initial sequence number, tells B. B chooses a different or possibly a different initial sequence number and tells A. And then we use those initial sequence numbers as we send our data. The initial sequence number does not have to be 0. It's usually larger than the last sequence number used in a previous connection. I connect to the Google web server, transfer some data. Maybe the last sequence number I used was 3061. 1 minute later, I connect to the Google web server again, transfer the data. Maybe the initial sequence number is 3062, larger than the previous one used. Instead of going back to 0 all the time, we'll often continue on. Importantly, and different from what we've seen in the past, each byte of data has a sequence number, and that sequence number is relative to the initial sequence number. Let's try and explain these concepts with an example. Do we have an example? Where? We'll go through connection establishment first. Before the example, so the main point, TCP segments have a sequence number. Before we transfer data, we need to establish a connection and agree upon initial sequence numbers. The source will choose an initial sequence number, as will the destination. How does that work? Well, that happens in the TCP connection establishment phase. Before we transfer data, there's some steps to synchronize the initial sequence numbers. The client tells the server its initial sequence number. The server tells the client its own initial sequence number. They synchronize them. So we establish a connection. Establishing a connection also allows to check that the other one exists and is ready to transfer data. I want to connect to the web server. I establish a connection to TCP at this device. If TCP is not ready to accept any more data, it may not accept the connection. If something's wrong at this computer, then it may say, no, you cannot transfer data. If we do accept a connection, then at the receiver we may allocate some memory for that connection, some buffer space. So that's the purpose of the connection establishment. TCP uses what's called a three-way handshake. Three-way handshake means there are three messages to complete the connection establishment. A handshake is to agree upon something. A two-way handshake has problems if we use a two-way handshake, just using two messages. We don't have time to explain the problems with a two-way handshake. We'll just go through how TCP does it. The handshake has three messages, three TCP segments. The first TCP segment, we set the SYN flag to be true, to be 1. In the responding TCP segment, we set the SYN flag to be true as well as an ACK flag to be true. We sometimes refer to it as a SYN-ACK segment. And in the last of the three is simply an ACK flag is true. Let's show that. That's the TCP three-way handshake. Node A wants to communicate with node B. It wants to establish a connection so it can transfer data. Before it can transfer data, it must perform these three steps. A sends a TCP segment to B. The flags that are set to true are simply the SYN flag in this segment. And the sequence number in the header is set to the initial sequence number chosen by A. I'll draw an example to illustrate that. So time increases as we go down. A wants to connect to B. So A chooses an initial sequence number, referred to in this diagram as ISN A, the initial sequence number chosen by A. And let's choose the number 361. The number it chooses may depend upon what's happened in the past. I just chose a random value here. And it creates a TCP segment and transmits that to B. In the TCP segment, in the header, the SYN flag is set to 1, which means that this segment is used to synchronize sequence numbers. SYN is short for synchronize. The sequence number field is set to 361, the value of ISNA. And the other fields are set appropriately. That is the destination port, and all the other fields would be set depending upon what's being used at A and B. We're just focusing on how the three-way handshake works. Send a TCP segment to B. When B receives this, B knows that A wants to connect to B. So if we accept the connection, yes, we would like to connect with A as well, we respond with a TCP segment. We make note of the sequence number, the initial sequence number chosen by A, 361, and we choose our own initial sequence number. some other number. They don't have to be the same, they're not related. And we send back one TCP segment, but that segment has two meanings, two purposes. The first purpose is to synchronize our initial sequence number. So we set the SYN flag to 1, and we set the sequence number to 1432. That is, A tells B its initial sequence number, B tells A its initial sequence number. But this segment also acknowledges the one that we receive from A. That is, B wants to tell A its initial sequence number, and it also wants to tell A that the initial sequence number A chose, 361, is okay, is accepted. So it sets the ACK flag to 1, because this is an acknowledgement. It's going to acknowledge the previous segment received, and it sets the ACK number, AN, to 1 more than the initial sequence number chosen by A. Go back just to remind about the fields. This is the TCP segment. The fields we're focusing on, sequence number, that was sent here and here, are set to a value. The flags are just 1-bit values. If they are set to bit 1, then it means that that flag is on. In this case, SYN was set to 1, all other flags set to 0. I just didn't write them. In this case, SYN is set to 1, ACK is set to 1 as well, meaning this is a synchronized message, this is a synchronized message as well as an ACK message. And the acknowledgement number field. If we set the ACK flag to 1, the value in the acknowledgement number field matters. We need to note what this value is. So we send that. Where the acknowledgement number is the initial sequence number chosen by A plus 1, 362 in this example. When A receives that, A knows that B has accepted its initial sequence number. A chose 361, acknowledgement is 362, everything's okay. A also knows the initial sequence number chosen from B, 1432, and acknowledges that. So the final message, the third message, is we set the ACK flag to 1 and the acknowledgement number to 1433. Acknowledging this sequence number received. Once B receives this, B knows that A has accepted its initial sequence number, and B also knows A's initial sequence number. So A has the initial sequence number of A, which it chose, of 361. And the initial sequence number of B, which it learnt from this message. And similar, B has those same values. It knows those values. The role of this process is to agree upon those initial sequence numbers, to inform the other side. And if for some reason they don't want to establish a connection, they can send back another type of message to say no. You can use a fin or a reset message. We're not going to cover that. This is the normal case where the connection is accepted. Tell B your initial sequence number. B tells you your initial sequence number, as well as acknowledges the one you chose. And then you acknowledge B's initial sequence number. Why do we have two different initial sequence numbers? Because once we set up a connection, A is allowed to send data to B, and B is allowed to send data to A. independently. A may send 1 million bytes to B, B may send 363 bytes to A. That data may be coming in at different times, and they will use independent sequence numbers to keep track of the data coming in each direction. For the data that A sends to B, we will start from 361. For the data coming from B to A, it will start from 1432. And those numbers will increase independently depending on how the data flows across that connection. This is the three-way handshake of TCP. Once we've done this, we can transfer data in either direction. So this is the general approach where we use some ISNA. Here's a specific example where I chose some random numbers for this example. If I keep drawing this diagram, and now A sends a segment to B and it contains some data. So to TCP segment contains some data. What's the sequence number? A sends, after those three messages, A sends some data to B. What's the value of the sequence number? What do you think? A sends some data now to B. Again? 363. No. Close. 362. We've always said about acknowledgements. Send some data, and acknowledgement says what's the next sequence number expected. Same meaning here. Send initial sequence number 361. Acknowledgement says next one I expect is 362. So in fact, the first sequence number sent that contains data is 362. The initial sequence number is one less than that. So the first piece of data is going to contain sequence number 362. If B sends data, then its sequence number will be 1433. If this contained an acknowledgement, that is, A sends data to B, B sends data to A, and also B acknowledges the data it just received, it would set the ACK flag to 1 and include an acknowledgement number here. Any guess on what the acknowledgement number will be? 363 is wrong. In what we've studied in the past, that's correct. That is, if we send 362, B sends back 363 as the acknowledgement. But that's not how TCP works. TCP sequence number count bytes, not segments. If we're counting segments, then yes, this is 362, ACK would be 363. But TCP sequence numbers count bytes. If this data contained 1,000 bytes, then you can think of the first byte as 362. The last byte would be, so it would go from 362 up to 1361. 1,000 bytes. So in fact, the acknowledgement number would be 1632. So that's the difference from what we've seen before. In TCP, the sequence numbers count bytes, not segments. Therefore, the acknowledgement number depends upon how many bytes we received, how many bytes were sent here. If it was 1,000 bytes, ACK would be 1362. If it was 2,000 bytes, it would be 2362. It was just 1 byte, we'll have what 363, like we said before. So that's something that we haven't seen before and adds some complexity in the understanding of TCP. Sequence numbers count bytes, not segments. We set up a connection. We may close a connection after we transfer data. We use fin flags to say we close a connection. What we'll look at next week is how do we transfer data, and we'll come back to this point of how do we count bytes using sequence numbers to transfer. So we'll explain this one again of why is this 1362. We'll cover that next week. So let's continue with TCP. So next week's our last week of lectures. We'll finish on TCP and maybe very quick on internet applications. Even if we get started, we'll be very quick on that.